In my Claisen rearrangement video, I gave you this question at the end as the challenge question. So let's look at this mechanism now. I'm going to start by redrawing my starting material and showing my sodium hydroxide. Sodium is just a counter ion, so it doesn't really matter here, and the hydroxide is my base. Since phenols are somewhat acidic, the first step here is going to be a simple acid-base reaction where my base comes in, pulls that proton off, and gives me corresponding alkoxide. Well, phenoxide in this case actually. Also, we are going to get water here as our co-product, and if we think about how favorable this proton transfer is, well, the pKa of the phenol is somewhere around 10, pKa of water, let's say it's 16 if we round that, which means that the equilibrium constant in this case is going to be 10 to the 16th minus 10 to the 10th, which gives us roughly 10 to the 6th power, which is a highly favorable reaction. So that means that I don't actually need a stronger base. Sodium hydroxide is perfectly capable of deprotonating my molecule and giving me the corresponding alkoxide, phenoxide in this particular case. Then, as I bring my alkyl halide, allyl bromide in this case, I am going to see a simple SN2 reaction, so I'm going to show this SN2 attack here like so, and as a result of this SN2 reaction, I'm going to get the following product, where I have just formed a new carbon-carbon bond right over here, so I'm going to say that this is my new bond. Now at this point I can see that this part of the molecule can undergo the Claisen rearrangement, so in order to make my life a little bit easier, I'm going to redraw the molecule, and I will number my atoms as 1, 2, 3, 4, 5, and 6. So in the course of this Claisen rearrangement, it doesn't really matter how electrons move around, so I'm going to show it like this. I'm going to end up making a new bond between my carbons 6 and 1 and break a bond between oxygen, which is my atom number 4, and carbon number 3, effectively migrating my allyl group to the nearby atom. So my atoms 1, 2, and 3 are here, oxygen is my atom number 4, then I have my atom number 5 and my atom number 6. Now, normally at the end of this step we would have a keto-enol tautomerism to give us the phenol back. However, in this case we do not have a hydrogen in this alpha position, and no hydrogen, no keto-enol tautomerism, which means that we are actually going to keep on going with this reaction, because now I have this part of my molecule which I could classify as a 1,5-diene, so that means that that part of the molecule can undergo the cope rearrangement. So again, to make my life easier, I'm going to redraw my molecule like so, and I'm going to renumber my atoms as 1, 2, 3, 4, 5, and 6. So now I'm going to be making a new bond between my atoms 1 and 6 and breaking a bond between 4 and 3. So my curved arrows are going to go, this one goes here, this one goes here, and that one goes there, giving me the following molecule. Now, in this case, I do have a hydrogen in position over here, which means that I can undergo the keto-enol tautomerism. I am not going to show the mechanism for that here, but I will squeeze my final product over there, and that is my final product. So as I've mentioned before, never stop after you identify one reaction. Always check if your molecule can cascade into further reaction and do something else. Like in this case, we ended up with the cascade of the Claisen rearrangement, followed by the cope rearrangement, and then we did the keto-enol tautomerism. Pretty cool, right? And as always, thank you for watching. If you like this video, hit that like button and subscribe for more. Check out this video next, and I will see you next time.